So, thanks for the introduction and welcome to our talk about cLuster. So, what was the motivation to do our talk, to do our work here? When you look at large interactive surfaces, you see that selection, rearrangement, and so on can be quite fatiguing. You have to do big movements that are tedious, and you have to put things on the side and just to reorder them. So we wanted to streamline this process. So what we did is we clustered the whole page in advance in order to do a more smart rearrangement strategy. How did we do that? So the first thing that we started with is to understand what sensible groupings are. So we conducted a background study to get to know that. Then we fed an algorithm with our diverse perspectives that we gained from the users. And once we had that algorithm, we tried to come up with an interaction concept so that people could actually use the algorithm that we developed. After doing that, we wanted to check the performance. So would the algorithm really get to do the things that the users expect from them? And finally, once we had approved that to a certain degree, we looked at use cases. So what is the algorithm good for besides just clustering, but can we go a step further with rearranging? And now I'll start with explaining you the background study. So how do actually people want their sketches to be clustered? So what do people expect as a result? And the second thing that we wanted to answer here is it actually just one correct clustering for each sketch, or are there many solutions that we might have to consider? So we started off with a huge number of sketches that we captured at our own research group and also from an external company. And these sketches were done on large interactive whiteboards over 2 years by more than 15 persons, so we had quite a nice variety here, which comes from team meetings, workshops, brainstorming, note-taking sessions, and so on. And the question now is, well, we have to burn it down a bit to give it to the users. So they can't really look at 300 sketches, obviously, so we had to find some sort of a categorization method. And we found that by Volny et al., who did some analysis on that topic, and we came up with a slightly modified taxonomy here, which gives us 7 categories of sketches, ranging from more written words to very figural sketches. So we analyzed our sketches here and saw that actually the amount that we have is quite different. So we have a lot of word lists, which means bullet lists, a lot of diagrams with sketches as labels, but much less sentences that are written out, obviously. Nevertheless, it gave us some sample to burn it down to 15 sketches, so we took 2 of each with 1 exception and also tried to accommodate for different authors and different styles here. So finally we had the 15 sketches that we came to look at in the background study, and we had 14 participants to look at that, with novice users to expert users, and we asked them to cluster the pages in different ways as they could imagine it, and also to name the way of how they clustered it. So to see what are they actually thinking when they're doing it. Overall, we figured that participants found roughly 2.3 ways to cluster each sketch. And to give you an example of that, here we see a sketch that depicts 6 scenarios. And one obvious way is to cluster the 6 scenarios. It looks a bit like a storyboard here. So we have the visual subgroups. But another way would be to go for more structural similarity. So have the text clustered and also have the figures clustered. A third way of doing that for this sketch would be to cluster each object and still have the text there. So as you see, there are different ways how to do that. And what we saw is that there are about 9 perspectives of how people are doing these clusterings. And once we look at the occurrences, we see that the 3 that I just showed you are the most common ones, while there exists also other types like columns, rows, which are very easy to depict. We didn't use all of those 9 perspectives in our algorithm. We omitted global and categories. Global because it was basically just that people said, well, this sketch can't be clustered, it's just one big giant chunk. And categories, first, because it was only very minor in its occurrence, and second, it goes more on semantic principles. So to summarize our background study, we gained 7 perspectives to train our clustering algorithm from. We also found, which was quite pleasing, that perspectives are quite universal. So they fit into multiple categories. And we also saw that experts are actually finding more perspective than novice users, giving us a proof that this is important to tackle. And now I'll hand over to Martin, who will explain the algorithm in detail.
Well, hello. So I'm here to explain how our tool works. The core of the tool is single linkage agglomerative clustering, which is hierarchical bottom-up clustering, where initial clusters consisting of single strokes are created first, and then iteratively in each step, two closest clusters are meshed together. Therefore, a tree structure called dendrogram is built. The tricky thing here is to define the distance between two strokes. Here we build on method by Delay and Lee, where they defined this as a weighted sum of simpler geometrical features. And the parameters of this distance function, the weights of the features, can be trained from the annotated data. And about the features, we use the difference of the properties of the strokes, like the width or height, or the distance between the centroids of the strokes, or overlap of the bounding boxes, etc., etc. In sum, we use over 20 of such simple features. Now I would like to illustrate how this clustering works. So let's say that we have these three characters, actually consisting of 5 strokes. In the first step, the singleton clusters are created, and then iteratively, the tree is built by merging the closest clusters together, eventually getting only one cluster containing all the strokes. There is a very important parameter, which is distance threshold, and it says where the dendrogram should be cut to obtain the final clustering. This threshold affects the granularity of the resulting clusters. Lower threshold implies more and smaller clusters, where higher threshold implies fewer and bigger clusters. Now about the training. There is an algorithm which can estimate the optimal parameters of the distance functions, the weights of the features, and the threshold at the same time. The parameters of the distance function define the shape of the dendrogram, while the threshold says where it should be cut. Now suppose that this is my annotation. A and B should be together and C separated. This annotation gives us 2 pieces of information. First one is an M-link, and it's a link connecting 2 subclusters of the annotated cluster. And actually it's the last link created to obtain this annotated cluster. Therefore, its distance is the maximum. The second piece of information is a C-link, and actually it links the annotated cluster with the closest another annotated cluster. And these 2 links give us 2 constraints. The distance of the M-link must be smaller than the threshold, while the distance of the C-link must be bigger. So it's an optimization task, and by solving it, we can obtain the optimal parameters, which gives us the expected result. To do that, we need a lot of data and a lot of time. But as you probably noticed, having this one dendrogram, we cannot get all the possible clusterings. For example, if I want A and C together and B separated, no matter what value of the threshold I choose, I cannot get it. So that's why we trained this clustering algorithm for every single perspective from our background study. Here you can see that if I choose third perspective, I can get what I want, A and C together, B separated. But in practice, it's not always so straightforward. Often, we need to combine these perspectives together to obtain the desired result, which can vary from time to time, from case to case. So how we do it is that we define new distance function, which is basically a linear combination of the distance functions from individual perspectives. And we need to find the coefficients of this linear combination. It might be tricky, so we let the user to make an initial selection. Based on the information of this initial selection, the algorithm estimates the parameters and makes the similar selections. And how it works? Actually, this initial selection is an annotation with very limited information. Precisely, there is one M-link and one C-link. It's not enough to train everything from scratch, but we are actually only combining these well-trained perspectives together. And it turned out that it's sufficient in most of the cases. And the advantage is that this estimation can be done in real time because we are processing only little of data. So our tool requires interaction with the user. Now let me show you how it works in practice. When the user selects the initial cluster, the parameters are estimated, and the tool makes the selections which are similar to the initial one. So when the user selects one object, the algorithm selects similar objects. When the user selects a group of objects, it selects similar groups of objects. And when the user selects objects in a column, the column perspective becomes dominant, and other columns are selected. And it works the same way for the rows. Of course, sometimes it's necessary to update the clusters. It can be done using simple gestures. For example, clusters can be merged by drawing a connecting stroke over 2 or more clusters. On the other hand, one cluster may be split, drawing a splitting stroke over one cluster. If the user makes a mistake, the gesture can be reverted by retracing the stroke back and then continue. And eventually, if it goes really wrong, whole gesture can be canceled by making a scribble at the end. So right now, it's everything from me, so Florian can finish the presentation. Thank you.
Okay. So once we had that algorithm, we, of course, were interested in how it performs. So we came back to the original data that we had, and we obviously put away those 15 sketches and trained the rest of them in order to use them as a training set for our algorithm. So now we fed this into our algorithm and had a trained algorithm, and we came then back to actually confirm what users did. So we wanted to see if the algorithm could do the same thing with those sketches. So we tested always the 2 most common perspectives that users identified if their algorithm would also come up with the same result. Doing that, we used 3 different initial elections to get some variety here. Following this, we had to think of any metric that would allow us to measure the success. So what we did is we used the steps of necessary correction to see how well the algorithm performed in each case. And there are 2 possibilities of correction. One is to adjust the threshold manually. The other one would be to split or to merge individual clusters like we have seen it in the videos. For instance, here we see an example that was used in the study, and we see that the algorithm can actually really nicely detect all those different columns. So we have actually a perfect example here. Well, a different perspective on the same example would be to have all the bullet points selected. And here we can see that just in the middle here, we have 2 arrows. So we have 2 bullet points combined. Using the split tool, it's not really a big deal to just split them. Nevertheless, we have now 2 additional steps that we require to fix this example. So overall, the results show that we have almost 50% where it can be done without any additional step or with just one. Having this confirmation, we went on and explored different use cases where the algorithm could be used for. So what are the possibilities? Well, besides clustering an entire page, we could do different things here. For instance, we could also give some sort of a preview for a selection. So, for instance, have nearby clusters just added in some sort of a temporal cluster and then confirming that if the user wants that. Another possibility is to mimic basically a text editing tool and add nearby clusters with a flicking gesture. Where the algorithm really works nicely is rearranging entire sketches. So we now do a clustering that actually clusters all the different furnitures here in this 2.5D drawing, and we can mirror them and just move them around to rearrange things very easily, just in a sketch content. But actually, we can go one step further. We can also move the clusters that we are not controlling directly. So we can, for instance, move them out of the way for a spring strategy, and they would just try to maintain their position as closely as possible. Nevertheless, it would be somehow helpful not to do this all manually. And if we have a more confined space of interaction, for instance, a storyboard or a bullet point list, we can use the bubble strategy, which just exchanges 2 clusters and so allows easy rearrangement. So summarizing, we did a background study trained our algorithm on that, then come up with a way of interacting with initial clusters for temporary selections, and utilize this in a use case. And if you want to see this in action, please visit our demo at the reception tonight. So thanks for your attention, and we are now happy to take your questions.
Hi, Dan Vogel from the University of Waterloo. It's amazing. It almost looks like magic, which is great. I think that's always a good sign that things are working. So your study is based on freestyle sketches on large screens. Have you thought about drawing tools like Illustrator? Like I use Illustrator a lot, and I have a lot of the same problems that I can't really find one group that covers all my different use cases I want to use. Have you looked at, or maybe you should look at this, more, like Adobe Illustrator, maybe even AutoCAD, these kind of drawing tools? And what would change? What do you think might change?
Well, I think we work ourselves with Illustrator quite a bit, but I think one of the key things here is that for sketching it has to go quite fast. So this was our main motivation to apply to this domain, while for Illustrator it's more a tool that you use on your own workstation, where you have very sophisticated tools and you want to have it at the right spot exactly, and you don't mind maybe so much spending this a bit of additional effort. But anyway, it would be of course a great possibility to also try to deploy to such tools if it would improve the speed there.
Yeah, because I do mind. It is extra effort for me. I think you have a possible solution here, so you could save me some time. Thanks.
Thank you.
Dong from Cornell, awesome job. I think this would magically work when the sketches are marginally well organized and good for clustering. But one daunting thing to categorize in the freeform sketch is the connecting lines between different categories. So how do your algorithm work in coordination with the connecting lines? Can your algorithm detect connecting lines, or will even categorize it?
Well, we are not detecting anything. That's the problem, because at first we don't expect that there be connecting lines or anything. We just had these 7 perspectives, and if the user makes the initial selection saying that, okay, that connecting line should be, I don't know, somehow separated, it tries to find out perspectives where this was similar and use this similarity from this perspective to give the desired result. If you have a domain where you expect that there will be connecting lines, it's probably better to use some specialized algorithm which can really detect these connectors.
Okay, for example, in mind maps, then...
In what?
Mind maps, then...
Yeah, definitely. If you have this knowledge of domain, you should use it. Maybe, in this case, it would be better to recognize what is the domain and then apply some specialized tool. This is for really free-form sketch when you have some subgroups and you can choose if you prefer columns, rows, some compact groups, or these things.
Thanks, perfect.
One very quick question, and then we'll switch to the rest. Have you tried using it where you have different people's sketches all? Because one person's sketching has a certain style, and the focus would be on different categories, whereas different people making different sketches have very different styles, and that might overwhelm your algorithm. Does it?
No, actually, this wasn't so much of a problem. We had a lot of sketches from different people where we trained it. What's true actually is that the sketching style from a person might help to do recognition. So we also deployed it to some design studios and let them try it out. And we had actually one person who was drawing with very long lines. So basically the whole table was just one long line. And obviously, I mean, this is great. This is like super easy to do. And others who would draw with much more small strokes, it would definitely be more challenging here. So that has an impact, but it's not really a big problem if they, over a large number of people.